In these two examples, we are going to be trying to find the areas under curves of both having fractions, but both going to be very different approaches to it. On this one, I'm looking and I see this kind of has, if I were to think, where did it come from? This has a chain rule kind of a feel to it, right? And another piece that I'm looking for is if it has a chain rule feel to it, and if I take the derivative of this inside piece, I get the outside, then that screams U substitution. So I'm going to take this x squared plus 1 and let that be my U substitution, because when I do the derivative of it, I get a 2x dx, and there's my 2x. It matches wonderfully. It's not even the number in the front. It's not the coefficient that matters as much as the power. I take the derivative of an x squared and I get an x. Perfect. So then now I'm going to take the derivative of x squared and get an x. So let me rewrite this a little bit to help my substitution. So I'm always going to pull off the numerator. So x squared plus 1 squared. And then I'm going to pull that numerator off and mix it with the dx. And there's perfect my 2x dx. So I can replace that whole piece with a du. And this was going from 0 to 2. And so that's going to become du. And this piece is going to become my u, but it's still going to be raised to the second power. So 1 over u squared, and this is du. All right, now since I turned it into terms of u, I need to change my bounds also in terms of u. Right now they're in terms of x's. Well, I have a nice little equation that I can take that x value and plug it in, and I take 2 squared plus 1, so that's 4 plus 1 is 5. And that's my new value, my new u value, because u is going to equal plugging that in. And if I plug in 0, I'm going to get a 1 out of that. So I'm going to go from a 1 to a 5 if I leave things in terms of u, and I am. So let me rewrite this to make this easier to do the antiderivative for. This is going to be a u to the negative 2, and then I will add a power. If I add a power, I get a negative 1, and I divide by that power. I'm going to get this going from 1 to 5. And so now if I kind of rewrite this stuff to kind of figure out what do I need to do, if I rewrite all of this, I'm going to have a negative 1 over u from 1 to 5. So that's really the math that I'm about to do. So we'll plug in the 5. We get a negative 1 over 5 minus a negative 1 over 1. So that's going to be a negative 1/5 plus 5/5, which is just going to become a 4/5. So that's the area under that original problem's curve. All right, next one. So this one does not work like this one, because if I do the derivative of the bottom, I do not get, I don't get an x. I mean, I would get an x, and I don't have an x anywhere on here. So it's not a nice u substitution like that. But what I will do is any constant, like I kept that constant on there just for a second because I saw that it was going to end up matching. But this one, we're not going to do kind of what we just did. So I'm going to rewrite this by pulling the 4 off. And I have a 1 over root 3 and a 1 over 3. And it's a 1 over 9x squared plus 1 dx. All right, so here's where it's going to go a little different than what we did on this one. This is going to become something that I don't take the derivative of x squared because there's no x up here. So it ends up being a substitution. It is this one right here. So it's going to be an inverse tangent, but I'm going to have to figure out these other pieces to it because it's not as straightforward. So first off, I need an x squared. We don't have an x squared. We have a 9x squared. So that means that that came from a 3x that was squared. So that I'm going to let be my u. So it's going to be a kind of a mini u substitution. So I'm going to let u equal 3x. Du is going to equal 3 dx. and I'll divide the 3 over. 1/3 du is equal to dx. Okay, because I don't have a 3 dx. Even if I pulled the 4 and connected it with the dx, I don't have a 3 dx. So I don't have this really nice substitution that we had going on with this. So then I'll just move the 3 over. So what I do have is a 4. I'm going to replace dx with 1/3 du. I'm going to pull the 1/3 out and combine it with the 4. And then the only thing that changed on this was this 9x squared, which I rewrote as a 3x, that whole thing being squared, I'm going to rewrite as a u squared plus 1 du. All right. I also messed with my bounds. Anytime that I'm going to leave everything in terms of u, just like we did over here, I'm going to need to take those values and plug it in, take that value and plug it in, and then go ahead and see what it switches to. So if I were to take the 1 over root 3 and multiply it by 3, I'm now going to get a 3 over root 3. And I'm going to rationalize that. So I multiply it by a root 3. So that becomes a 3 root 3 over 3, better known as a root 3 over 1. So root 3 over 1, or just a root 3. And then my other one is taking a 1/3 and multiplying it by 3. That's just going to become a 1. So those are my new bounds. All right, so now that is in the form that I want. I want it to look like that. And so I have this u squared. My a squared is a 1. So my a value would be a 1. That's what I would square to build that. And I need that because I need to put those in the denominators. It really isn't going to do anything. If it was like a 4 squared, then I would be subbing in different values and we would get fractions. But we're just replacing with a 1. So at this step, we have a 4/3. This value is here. And so we're going to be replacing this with a 1 over 1. So then that's just going to be 1 over 1, which I can just leave it out. Inverse tangent of u over 1, which we'll just write as u. That's it for that. And then we're going to go from 1 to root 3. Okay, so now I need to plug some values in. So now we're going to do our 4/3. We're going to be doing the inverse tangent of root 3 minus the inverse tangent of 1. Got to figure out what those values are. So I'm thinking of 2 triangles that I can kind of work with. Triangle that has a root 3 is a 30, 60, 90. And so I have a 1, 2, and a root 3. So tangent of, this is a 30 and a 60. So tangent of 60 is going to give me an opposite and an adjacent equal to this. So when I'm undoing a tangent, I'm finding an angle value, but I want the radian version of that. And so that value is going to be pi over 3 minus inverse tangent of 1. Either I think of a 45, 45, 90, or maybe the graph of that. But I know that I can get an opposite and adjacent. The only time that an opposite and adjacent simplify to 1 is when I do tangent of 45. So this is going to be a pi over 4. And then I'm going to distribute it 4/3. So now we just kind of have some algebra that we got to put stuff together. So I'll distribute it 4/3 here in a minute. This, I need a common denominator, so I'm going to multiply by 4. So 4/12 multiplied by 3 minus 3/12. And that's going to be 1/12 multiplied by 4/3. And that 4 can simplify with that 12. So my final area under that curve is going to be pi over 9. All right, so that was a couple different types of situations with finding areas in a curve with some u substitution.